So the last class we have been talking about something called global reactions, and what we found about global reactions was that they do not really happen in reality. They are happening at some sort of like a conceptual level in our minds, and we are trying to represent what is happening in reality at the molecular level by these global reactions, and therefore the kinetic parameters need to be obtained empirically for the considered species in those global reactions. We also found that global reactions need not be single step, they could be multi-step as well, in order to take into account some of the intermediates that are not necessarily highly unstable, but those that we want to keep track of for some purposes. But in reality what we are having is reactions actually happening at the molecular level, and these are what we call as elementary reaction steps. So if you have to consider reactions happening at the elementary reaction level, then what we have to do is we have to look at what's called as detailed chemistry. So in general what happens with these reactions is there are typically a huge number of reactions that happen and involve a considerable number of species. Okay. So typical numbers we are looking at are tens of species or maybe up to 100 species, and maybe about close to 100 or more, okay, or few hundreds of reactions that are happening. Now many times it's either difficult for us to actually know what these reactions are, or second thing is it's difficult to actually get the kinetic parameters for each of those reactions. Okay, so these are the first two steps for us to actually get information from the chemical kineticists. The third problem is, let us suppose that the chemical kineticists were able to actually give you everything that they could possibly give, right, and let us say that they say, okay, you are looking at this reaction mechanism and it involves at least about 1000 reactions, these are all the reactions and these are all the kinetic constants for those. The question is, can we handle them? Right. So many times it is not possible for us to handle so many reactions in the first place, number one. Number two, we may not need to handle all the reactions as well. Okay, so just because that is what is happening in reality does not mean that we have to from an engineering point of view consider all of them, right. So many times what's typically adopted is reduced mechanisms. Reduced mechanisms are most often adopted. So the difference between reduced mechanisms and global reactions are, reduced mechanisms still involve a reduced set of elementary reaction steps at the molecular level, right. Therefore we use molecularity in the law of mass action, right. That is, we do not use orders for the reactants, in the law of mass action, we actually can go ahead and use molecularity for writing out the reaction rates for each of those elementary reaction steps in a reduced set, right, so that there is no ambiguity there about what we need to do. And other than obtaining the reactions themselves from an empirical manner, or getting the kinetic constants empirically even for the molecular level reactions, we are not necessarily looking at empiricism in order to get the orders. It's basically based on what happens at the molecular level, so we just use molecularities rather than orders there. But the key is, what is this reduced set, right? How do you determine this reduced set? Now that is actually something that is very difficult. We don't want to get into that in this course. So reduced mechanisms are determined in a number of ways. The easiest, I'm not going to say anything much more about this, but the easiest for us to think about is look at the rate determining step. Okay. The rate determining step is typically the slowest step that's happening. So if you now have a sequence of reactions that are happening, right, so I have now a example of a reduced set that is put up here, right, for something as innocuous or very simple as a hydrogen oxygen system, and you would think that it's only hydrogen and oxygen, there is nothing more, right, but look at how many things that are going on over there. And this is like one typical example of a reduced set of reactions that are happening with just hydrogen and oxygen to get you water. That's the ultimate goal. Okay, so we are looking at a global reaction as H2 plus half O2 gives water or something like that, but in reality you are having at least 9 reactions that we need to consider for doing something sensible. Typically how it is being done, first of all what we have to look for is what is initiating this. So there must be like one reaction or at least 1 or 2 reactions that initiates the reaction. That means you start with a stable reactant and M corresponds to any species that this can bombard with. So it could be itself, it could be O2 to begin with, or once this has got started this reaction would still be happening, so it could be any of those, OH or O or H or those, or even walls of the vessel, okay, like the surface, right. And many times we have a dilemma. For example, if M is like a gas phase species, then its concentration is important in determining the rate of this reaction, okay, and we will go through these as we go along, but essentially that's how you start the reactions. That is, you now have one of the stable reactants begin to decompose into atomic level radicals or intermediates. So this is H, for example, is an intermediate. In the big global reaction that we are looking at, H2 plus O2 gives H2O in whatever proportions. H doesn't figure in, O doesn't figure in, OH doesn't figure in, HO2 doesn't figure in, right. So all these things are essentially then intermediates that we have to recognize as such. So you now have a chain initiation step. This is a chain reaction, and in all these things you have to start talking about chain initiation, chain branching, chain propagating, chain terminating, and so on. Okay, so it's actually a reaction chain that's happening, right. So when you say chain branching, what that means is it actually multiplies the number of intermediates. You see, you started out with one stable reactant, and one intermediate, but it results in two intermediates. That means it branches out. Okay, so the third one is also actually multiplying the number of intermediates. The propagating steps are sustaining the number of intermediates. That means you now start with H plus O2 plus M gives HO2 plus M. So it is like you had H to start with, O2 is stable, M is any third species which is staying there on the other side. You started with one intermediate, you are sticking with one intermediate. Okay, so you look at HO2 plus H2 gives H2O plus OH. H2 and H2O are stable, but HO2 and OH are intermediates. So you're now propagating. Okay, that means you're not really branching, you're not terminating, but you're just propagating. The number of intermediates keeps preserved, right? So those are the propagating steps, and finally we are also looking for some terminating steps. And in some of these propagating steps is when you're actually beginning to produce the final product, the stable product. Okay, so if you're really interested in finding out the rate of production of the final stable product in what you could think of the global reaction in your mind, you should keep these reactions. If you throw away the elementary reaction steps that are producing the final product in your reduced mechanism, then you are not producing what you want, right? So you'll have to keep these, and then you have to look at the rates at which these are happening, and then what happens. So you now look at H2O that's being produced, it's depending on the concentration of HO2 and the concentration of H2, concentration of OH. So you have to now look for those reactions which are producing OH and HO2. Alright. Now you might find that there is only one reaction that is producing HO2 when compared to a bunch of reactions that are producing OH. So obviously we might think that the route by which H2O is produced from HO2 is less important when compared to the route from which H2O is produced from OH. Okay, that's one way of thinking about it. The other way of thinking about it is look at the reaction that is producing HO2. It's a termolecular reaction. Okay, that means H and O2 have to bombard in the presence of M. That means three bodies have to collide for you to be able to produce this. This is a highly unstable intermediate, doesn't happen very prevalently, right? So the reason for that is termolecular reactions are important mainly at high pressures. So it's only at high pressures we are actually trying to put a lot of species together in a much more compact region because we are trying to pressurize, right? And that's when the probability of termolecular reactions actually increases, otherwise it's pretty low. Therefore we could say at moderate pressures or low pressures, let's not worry about this, for example, right? So these are the ways by which you would think about trying to pick some reactions over the others. Among these, one of the chief things that I am talking about is we now say K1, K2, K3 etc. Each of these has actually an Arrhenius expression that you can write which indicates the exponential dependence of these on temperature. So if you now have a temperature bath at which these reactions were to take place, in reality for the flames it does not happen that way. Okay, in reality for the flames the temperature continuously changes in space, and for unsteady problems, the way you want to pose unsteady problems, it might change in time, right? So it's not like a nice constant temperature bath. But if you want to do for kinetic purposes, think about a particular temperature at which you want to compare the rates at which these things are happening, which is what do you call simpler. It's actually simpler to think about that way. Okay, in reality it's possible that you have to have a chain, you know, like last time I said only if CO is produced can it get oxidized, and then it's going to compete with the oxygen that was used to produce it in the first place. Then in a flame you might find that depending upon the reaction rates of the two reactions that we are thinking about, they could be spatially displaced. You might have, like, as the reactants are coming in, you first have to have one reaction happen and then feed and convectively feed into the next reaction zone. So the reaction zones could be separate, it is not necessarily at the same place, and therefore the temperatures of these two reactions may be different, and depending upon the temperatures at which these two reactions are taking place, one of them could be faster than the other merely because the temperature was different, right. So comparing these things at the same temperature is not a very straightforward thing, but you could think about it from simpler for the purpose of simplicity, right. Let's say you did that. Other than having to sequence them, because one has to produce H in order for it to be utilized, okay. So keeping the sequence in mind, the next thing that you want to worry about is which one is actually the slowest, okay. So when many things are happening in parallel, okay, if you now want to say I want to look at the whole thing as like one black box, I am putting in hydrogen and oxygen here, I want to get water there, all this stuff is happening, tell me how fast this is going to happen, then all I am going to be thinking about is which of those reactions is the slowest to happen, that is the one that is going to determine the rate at which the whole thing is going to happen, right, because until that is complete I am not going to get out water, okay. So all other reactions could have already happened, but it is waiting for this last reaction to happen, you see. So the rate determining step is the one that is actually the slowest with the slowest reaction rate. So you could also pick these reduced mechanism reactions based on the reaction rates, okay, and a much more sophisticated way of doing these things is called rate ratio asymptotics. That is something that quite a few people have done in the last many decades to try to deduce reduced mechanisms, okay, to actually compare rates and then look at asymptotic expansions based on those and so on, and we do not want to go further into that because it's an area that can take pretty much all your time thinking about. So in what we have done, we have introduced a couple of ideas here. First of all, the right thing to do instead of adopting global reactions is to actually adopt reduced mechanisms, because the chemical reaction rates that you would want to write for the law of mass action would be less ambiguous. But then what could be ambiguous is to how to reduce the reaction mechanism, and there are people who work on this separately. So if it is possible for you to actually look at the literature for your application, let us say you are now looking at a partially premixed flame under some conditions or something like that, so a particular situation, there are people who work on this, do experiments and deduce these things and so on, and also do the analysis for this and try to recommend reduced mechanisms. Many times as we go along, between the time I graduated or I went to grad school to now, the last 15-20 years for example, things have actually grown. So previously when two reactions was considered to be too much, okay, now your chemist is going to say take these 50 reactions, okay, just take it, and then you really like, can I reduce further? Or maybe you do not have to, so you have computer power to handle those 50 reactions, so just go ahead and try to use it and so on. So it's an expanding area where things keep changing, what's required keeps changing with computer power and so on. So therefore the right thing to do is for you to actually try to keep as many elementary reaction steps as possible, because they are closer to reality. And the second thing that we have also come across is the nature in which these reactions happen, right. That is, they get initiated, they branch off, then propagate, then terminate, so that sequence, right. So in this sequence what's essentially crucial there is the role of intermediates, the presence, the formation, the presence and the role of the intermediates in each of these, because when we are now trying to identify a reaction as branching or propagating, we are actually looking at how many intermediates are showing up on either side, you see. So So we have now also started looking at intermediates as one of the important things in the reaction scheme. And finally I would like to point out that we now have a reaction scheme that put together is the one that's now going to give you the reaction rate expression that depends on the reactant concentrations for the stable reactants, the original reactants. So if you are now basically looking at H2 and O2 giving H2O, you finally want an expression for the rate of production of water which depends on the concentrations of H2 and O2, right. But that is something that you want to deduce from this entire soup of reactions. Water is happening here, it depends on this and this, this and this, so this depends on this, so it depends on this and this, depends on this and this, you keep going back ultimately to wherever you are showing up as H2 and O2, the reactants. So we want to, our job is finally to link up the rate of production of products to the rate of production of reactants through the rate of production of the net rate of production or depletion of the intermediates, right. And if you now are able to actually look at how my global activation energy, for example, is going to fare given the activation energies of all these, you see, because you have kinetic constants for these, and finally we want to deduce a kinetic constant for like a global reaction from this, let us suppose, right. What is going to happen is if you have more and more chain branching and propagating reactions, the global activation energy will come down. That means its sensitivity to temperature actually diminishes. So there is a role for consideration of detailed chemistry and the way you want to reduce the chemistry in how it influences your global activation energy or the net activation energy for the entire system. Net activation energy essentially tells you how the full system of water production from hydrogen and oxygen depends on temperature, right, how the nonlinear dependence is, right. So there is a significant impact that this has on the global performance of the system. What we will then do is come up with a couple of approximations which we can try out with these intermediates in trying to quickly put together this connection between rate of production of products and concentrations of the reactants. Okay, so let's get into that game of getting like a global reaction rate based on the reactant concentrations through the intermediates, right. So some easy ways of doing this is one, steady state approximation. Steady state approximation, right. So in steady state approximation what we are essentially saying is if you now are trying to plot your concentrations of different species with respect to time, right. Initially at t equal to 0 you are starting with a bunch of reactants at some concentrations. Let's say we have some reactant that we can follow, and as the reaction proceeds the reactant concentration will decline, right, with time. So that's not a, you don't get any prizes for this, right. And what happens to the concentration of the products? It will increase, right. How does it increase? It increases like that. It should increase like this because ultimately at t tending to infinity it does asymptote, right. So well, let us not worry about how if there is any inflection here and so on, but ultimately we are looking at a picture that will emerge like that. Now the story is about the intermediates, it is not about It's not about what happens when we are born or when we die, it's about like the life in between, huh? Right, so that's the intermediate's life. So all life is intermediate essentially. So question is, what do the intermediates do? They are born and they die, right, like all of us. So the question is, how do they behave? They have a maximum, right? So it goes and comes down. Does it go up and then come down immediately, or does it want to live for some time, like us? Right? So it does that, right? So the intermediates, you know, they are produced and then they want to stay for some time, as long as they can. So it's not really like a peak at the maximum, it's a plateau at the maximum. Okay, so they are produced and then they are like, yeah, I'm going to be here for quite some time, yeah, sure, let me have some fun. That's the way it goes, and then ultimately it dies. Okay, so what we are looking for is it possible for us to exploit the situation? Say, let's not worry about the initial transient when the intermediates are just beginning to get initiated and branch off, okay, or let's not worry about when they are busy getting terminated. Okay, can we look at the region when they were actually simply propagating, when the concentration is going to be more or less constant? And if that is the case, then we suppose that is around like a steady state, things are not changing with time, and so we approximate the concentration of an intermediate approximately equal to the rate of change of concentration of an intermediate with respect to time as approximately equal to 0, where A star is an intermediate. This is the this is the essence of the steady state approximation. Okay, so what do you get out of this is what we have to see, right? So we use this approximation to obtain global kinetic behavior What's meant by global kinetic behavior? That's like linking rate of production of final products to reactant concentration. To reactant concentration. That's like the global kinetic behavior, right? So let's suppose that we consider a first order reaction, first order global reaction. I'll put this within quotes, first order global reaction. A gives products. We don't really worry about what the products are because the law of mass action says that the reaction rate does not depend on the concentration of the products. It's only the reactants that we have to worry about. Not that we are really worrying significantly about the reactants, it's just A. Okay. So it's a template reaction, right? Now we could examine the following detail mechanism involving an intermediate, that means whenever you want to propose a theory, the quickest way to publish is to make your number of variables as little as possible, right. So just keep it one, huh? So you're looking at the role of intermediates, just keep an intermediate with you, don't get into the soup bowl of intermediates, right. So this is due to Lindemann. So let us suppose that we now have A plus A gives and takes A star plus A, and we denote the forward reaction by the rate constant Kf and the backward reaction by the rate constant Kb, and let us suppose that A star gives products. A star gives products, and let us call this second reaction rate constant as Kf prime, I'm sorry, Kf prime. This is actually a set of 3 reactions, okay. So A plus A gives A star plus A is one reaction, A star plus A gives A plus A is another reaction, okay, each of them having Kf and Kb as the rate constants respectively, and the third one is A star gives products with a rate constant of Kf prime. And let us suppose that this is actually, this set of reactions is fast and this one is the one that is slow. That means the moment you have A, it produces A star, and it now starts getting in equilibrium with this, right. The more A star it produces, A star combines with A to produce A back, therefore there is an equilibrium that can be associated with this, okay. So and then these things are happening very fast, so it's like you now finally have like some pool of A star. Now what's the job of A star? A star's job is to actually produce products, it's not A's job. A's job is only to produce A star and get into equilibrium with it. That's what the first 2 reactions do, producing A star and getting into equilibrium, okay. The third reaction is where the A star is the one that's producing the products, and that is slow, okay. So now we are beginning to think what would be the order, now think about this, what would be the order of the global reaction A giving products. That is what is supposed to happen, okay, and all this is like details that are happening in reality, okay. So let us now think about how to deduce this, okay. So the rate controlling reaction is the slow reaction, right. So which is unimolecular, A star giving products is a unimolecular reaction. Therefore we expect the mechanism to behave as a first order reaction globally, right, because it depends only on concentration of one of the species, okay. So what is meant by globally? Like for example, if you now think about these things as gases, which is what we have been doing all the time, right, the concentration of these is actually directly proportional to pressure, right. If you now had a bimolecular reaction, then the law of mass action will have a p squared. So the question is essentially, are you going to have the reaction reaction rate for the final global reaction go as linearly as p or square of p or somewhere in between, right? Order for the global reaction doesn't have to be an integer, right? So what is it going to be? So in fact a way to pose the problem a little bit more general is consider a global reaction n A gives products, okay, and we basically for the global reaction assign a value of n based on what's the order that is deduced from the detailed reactions, the elementary reaction steps, right. So question is then n equal to what? Is it supposed to be first order or second order or somewhere in between or what or anything else? That's exactly what you are thinking about, with this being the detailed mechanism in this case, okay. So but you see the first reaction is bimolecular, which implies reaction rate goes as p squared, and that's important for us to think about, because what is ultimately going to affect us as far as the reaction rate is concerned is the concentration of A raised to whatever the exponent is, and the concentration of A shows up in the first reaction, which is bimolecular, okay. Even though the second reaction is the slowest and therefore the rate determining step, it's actually in A star, so its reaction rate is going to actually depend on the concentration of A star rather than A. You look at the reaction that is actually depending on the concentration of A, the first reaction tells you it's bimolecular, right, which means it has to go as square of pressure, okay. And recall or note, okay, note that termolecular reactions have omega goes p cubed, okay. It's kind of like extending from bimolecular. If you have p squared, then termolecular reactions, of course we are not looking at termolecular reactions here, just mentioning this because what we have to consider is it is going to go as p or p squared, p cubed, okay. Then what happens is, if you now are working at a high pressure, then p squared is going to be a lot sensitive when compared to p, okay, or p cubed is going to be a lot more sensitive to pressure than p squared and then p. But if you are working at low pressures, so the pressures are low, p squared will be lower than p and p cubed will be still lower than p. You see that it becomes like anti-sensitive. The p cubed or the termolecular reactions now become a lot more sluggish when compared to, or they are sensitive in that sense that as you now decrease the pressure, they suddenly become or very drastically become less important, right, and it's the p squared ones are less important when compared to the p reactions. So here at normal pressures the forward and backward or reverse reactions, okay, reaction rates go as p squared, and third reaction rate go as p, but at very low pressures but at very low pressures, then the first one actually becomes slow. The first two reactions become slow, right? The first two slow down, and the third predominates, right? That's what we expect. That means we can't put a number to n for all pressures, depending upon the mechanism, which in this case we have considered a particular mechanism. We can see that the number for the order could be anywhere between 1 and 2. Okay, so normally it could be like a second order reaction. At low pressures it could actually behave more like a first order reaction. Okay, so you're now beginning to look at this possibility. So how do you demonstrate this? The answer is, we now try to adopt the steady state approximation. So we may write dCA over dt equal to minus kf Ca squared plus kb Ca star. So this is for the depletion of A, this is for the production of A. Okay, A is being depleted because of the first reaction, but it's being produced by the second reaction. Okay, this negative sign with the coefficient 1 takes care of the fact that we have 2 molecules of A consumed versus 1 molecule of A being produced even in the first reaction. So it is taking into account the fact that there is some partial production of A there. Alright, and still there is like a net depletion. That's the reason why you have a negative sign. And so let's now say this is 1, and dCA star divided by dt equals kf Ca squared minus, now A star is actually being is participating in 3 reactions. Okay, it's being produced in the first reaction and it's getting consumed in the second. There is a reverse reaction there, and the third, right? So kf Ca squared is actually the production rate for A star, but it is also getting depleted twice, which is kb Ca star minus kf prime Ca star. Let's call this 2, right? Our goal is to actually solve for Ca and Ca star. That's what we're supposed to do. Okay, and this is, as I said, a system of 2 simultaneous ODEs, and we have to supply initial conditions, and of course I can gladly tell you that Ca star initially is equal to 0. Okay, so I got it, and then I will supply some number for Ca, and starting from there you want to now march in time and then see how these things grow, and then try to fill up this graph essentially, right? That's what you're supposed to do. So what you could do is, you know, in this equation you could try to eliminate Ca star. Let's say you're not interested in Ca at all, Ca star at all. Okay, so you can eliminate your Ca star from these 2 equations, and then you can also try to get your dCA star over dt, which will involve a dCA by dt when you try to eliminate Ca star, and then plug for Ca star and dCA star by dt, and you now get like a humongous looking nonlinear second order ODE for Ca. That means you will have a d squared Ca by dt squared term. You could also potentially have, because you're showing up these squares and so on, you will also have some dCA by dt the whole squared terms, and then dCA by dt and so on. So you now have like one ODE which is like second order nonlinear in dCA by dt, okay, and then you can, if you can solve that. Okay, so trying to eliminate CA star and dCA star by dt from the above will result in a second order ODE nonlinear ODE for CA, right, that is CA star equal to KF CA squared plus dCA over dt divided by KB CA. That is something that you can get from 1, okay, let us call this 3, and dCA star divided by dt equal to KF divided by KB dCA over dt plus 1 over KB 1 over CA squared dCA over dt the whole squared plus 1 over CA d squared CA over dt squared, okay, and then you now try to put 3 and 4 back in 2, and then you will now get an equation that involves only CA and its derivatives, okay, but it is going to look so ugly that we do not want to consider it at all. Okay. Instead what we want to do is steady state approximation means that we now say dCA star divided by dt is approximately equal to 0. That is exactly what we started out with to consider, right. So do this and then we will try to take it up from here and see what we get next class.